Bismillahirrahmanirrahim. Today our lab is how to use arithmetic operators, logical operator, relational operators and other operators in Verilog HDL and how we can perform different operations by using these operators. So in today's lab we will see how we can implement these operators using Verilog HDL and perform different actions. So first of all, our first operators are arithmetic operators which can perform arithmetic operations. These are multiply, divide, plus, minus and modulus. The binary operators are multiply, divide, add, subtract and modulus, and here is the example which show how these operators can perform these operations. So here you see in this example, here is the declaration of module whose name is arith test and output and inputs are A, B, C, D, E, F, G, H. Next, in Verilog HDL we will declare the inputs whose bit size is 4 and inputs variable are A and B, and then we will declare the outputs whose bit size is 8 means 0 to 7 and output variables are C, D, E, F and G. Here in this example I am taking the value of A 12 and B 3 and I am representing here in this code by giving the in this code I have given these values A equals to 12 and B equals to 3 by just using the comment to show you the value of A and B input variables. Then I assign the C variable output and this can perform A multiplied by B, which means that it can perform the multiplication operation between the inputs and then store the value at the output variable C. Because here A is 12 and B is 3, so we will get the output at C is 001 001 00, and then I assign another output variable D which can perform the division operation between A and B, and the output at the D becomes 4. And similarly then I assign the E input output variable which can perform the addition operation between the operators input variables, and then our output is 15 at the output variable E. Then I assign another output variable D which can perform the subtraction operation between the operators, and our final output is G variable which can perform the modulus between the A input and B and give us the 1 at the output. And then we use the end module to end our program. So now I can perform this whole Verilog HDL code in the software and then show you the input and output combinations and waveform. Here you see I have written the code of arithmetic operator in Verilog HDL. Same is the context as given in the example. First of all we declare the module our whose name is arithmetic test and these are all our output and inputs. After that I have declared the inputs, then outputs, and then similarly input by commenting the A equals to 12, B equals to 3, and then these are our outputs. I have given the assign by giving the output C, D, E, F, G which can perform the multiplication, division, addition, subtraction and modulus, and now the end module which shows that our program is end. Now I will compile this program. Start compilation. You see here our compilation was successful with 0 error. If there was any error in the program then compilation was not going to successful and then error appears here. Now I will make the university program to generate the output waveforms. Here you see the waveform. Here I will insert the nodes because I need all the input and output nodes, so I will select all the nodes and here. Now I will assign the values to our input variables. I will assign the value 12 to the input A and here unsigned decimal and 3 to the input variable B. I have given the values to the input A and B. Now I will simulate this waveform. I will save this waveform and now the simulation starts. Here you can see the output waveforms of our output variables C, D, E, F, G. Here the outputs are represented in binary. Now I will change these binary to the unsigned decimal so you can easily verify the outputs. I have changed all the outputs to the unsigned decimal because output C is A multiplied by B, so you can see the output is 36, and the output D is A divided by B, so you can see the output is 4, and output is A plus B, and you can see the output is 15, which is 12 plus 3, and output F is A minus B, which is 9, and G is modulus of A and B, which is 1. So from this waveform outputs you can easily verify our arithmetic test, and here I have successfully implemented the arithmetic test code in Verilog HDL and can verify the outputs. Our next operators are logical operators. Here you can see the key symbols of logical operators, which is AND, OR and NOT. The logical operators are logical and logical OR and logical NOT. All logical operators evaluate to either true means 1, false means 0 or unknown X appears. An operator is true if it is non-zero and false if it is 0. An unknown or a high impedance value evaluates as false. So means that logical operators are AND, OR and NOT. A logical operator will give the true output when any of the output is 1. Means that when I am operating the AND operation, if both inputs are non-zero, then our output will be true, means 1. Or if in an operation, if any of the output is 0, then our output is 0. Here you can see the example of logical operators. The module declaration is name is logical and output and inputs are written here. After that I have declared the input variables and output variables and their bit sizes. Here in the by commenting I have given the values to A2, B0, C4, hexadecimal type and unknown. Here 4 represents the bit size of C input variable, H means that it is hexadecimal, and X represents that the bits are unknown. Then I have assigned the outputs assign output D and 2 and operands mean that input A and input B will perform the AND operation. AND operation by this that when both inputs are high, then the output will be true. If any of the input will be 0, then the output will be 0. Here you can see the input A is 2 and input B is 0. Because B is 0, so logical AND evaluates to 0. Then I have assigned the E output variable A or B. Because this is OR operation, so if any one of the input is non-zero, then the output will be non-zero. Because A is 2 and B is 0, we have the A non-zero, then logical OR evaluates to 1. Then I have assigned the another output variable F, which is equals to not of A, means that it will give a complement of A. Because A is high, so it will give us 0 and evaluates to 0. Then G equals to A or C. Because C is unknown, so this evaluates to 1 unknown. Because C is whatever 0 or high, our input is high, so this OR operation will always give us high without knowing the C input. And then I have assigned the output C, which is not of C because C is unknown, so this evaluates to unknown. And then AND module. We have the exercise for these operators, logical operator. Here I have written the codes for all of these A, B, C and D, and then by written the code in Verilog HDL, I have to prove these all. So now let's move to the Verilog HDL code. Here you see that I have written the code for the logical operators. I have the module whose name is logical operator, and these all are output and inputs. Then I have declared the inputs. Our A input is 8 bits and all other inputs are 4 bits. Then I have declared the outputs. Our output W is 8-bit number and all other outputs are 4-bit number. Then I have assigned the W, which is not of A, and then X, output X, which is equals to B and C, means that the AND operation between inputs B and C will give us the output at X, and then the OR operation between inputs D and E, which will give us the output Y. And then after that I have assigned the output Z, which is F or G and H, and then not of I. First of all the brackets will solve, then this OR operation will perform, and after that not of I, and then this OR operation, and after that our program will end. Now I will compile this program. I have to start compilation. Now compilation starts, and then after that compilation was successful, we will generate the waveforms. And in waveforms I will first assign the values to the inputs and then simulate the waveform and check the outputs. So wait for the simulation to complete. Our compilation was successful. Now I can generate the waveforms. Here I will select all the nodes because I want all the input and outputs on the screen. So I will select all the nodes. Now all the nodes appear here. Now by seeing this exercise, I have given the values 67, 0, 1, 1, 2. Now given the values to the input variables, I will change them to unsigned decimal so I can easily give values to input variables. I am giving the values to the input variables by seeing from the exercise. I have given the values to the all input variables. Now I will simulate this. I will save the waveform. Our simulation starts. Here you can see the output waveforms. At the output W, I A000 because output W is the not of A, and this will apply complement to the input A. So I will give output W to the 0, 0 and 0. And after that our next operation is X, which is B and C, because AND operation, if any of the input is low, so I will obtain 0 at the output. Because our B input is 0, so AND operation between B and C will generate the 0 output. Here you can see the 0 at the output, which is representing here. And after that I have performed OR operation between input D and E, so I will obtain 1 at the output Y, because input D is 1 and C is also 1, so 1 or 1 is 1. And after that I will obtain 1 at the output Z, which is shown here in the waveform. You can easily see that. So by just seeing the values at the output, you can easily verify these operators and can perform different operations using these operators. So this is our logical operators. Now our next operators are relational operators. Relational operators can relate the inputs variable, means that it can see whether the inputs are less than, greater than, equals to, or less than, equals to of each other. Here you can see the test case for the relational operator. I have given the module declaration input and output similarly as previous, and here our inputs are A, B, C and D, which are 2, 5, 2 and D is unknown. Here you can see that I have assigned the output E, which is A less than B. It can check that whether A is less than or greater than B. If A is less than B, which means that this operation is true, so it will generate the true on the output, means 1. If A will be greater than B, so it will generate the 0 as the output. Then it will check. Here I have checked the A, whether A is greater than B, so it will check the inputs, because input A is 2, B is 5, because A is not greater than B, so it will evaluate to false, means 0. And then G, which will check whether A is greater than equals to C, so A is 2, B, C is also 2. A is not greater than but it is equals to C. So it will evaluate to true. And then H output, which will see D whether D is less than or equals to A. A is 2 but D is unknown. So we can't check whether D is less than or equals to A because D is unknown. So it will evaluate to unknown at the output. Then our program ends. Now I will perform this task on the software. Now I have written the code for the relational operators. Same is the syntax for the code. First of all module, then input outputs, and then assign the outputs. I have explained you all the code. Now I will just simulate it. I have already compiled that code. Now I will generate the waveforms. Now I have to give in values to the inputs. Input A is 2, B is 5, C is also 2, and our input D is hexadecimal and unknown. So I have given the unknown to the input D. Now I will simulate it. Now our output appears. Here you can see our output E is to check whether A is less than equals to B or not, because A is less than equals to B, so E evaluates to 1. And our next output F is to check whether A is greater than B or not, because A is not greater than B, so it evaluates to 0. And our next output G is to check whether A is less than equals to C or not, because A is not less than but it is equals to C, so it evaluates to 1. And our next output is H is to check whether D is greater than equals to X A or not, because D is unknown. We cannot check whether it is greater than or equals to S, so this output will obtain unknown. So in this way we can perform any operation by using the relational operator between the inputs. Now our next operators are equality operators. The equality operators are logical equality, logical inequality, case equality, and case inequality. First of all, you have to know the difference between logical equality, inequality, and case equality and inequality. So the logical operators will return unknown if significant bits are unknown or high impedance. Means that logical operators just check the input variables whole and will give us the output. Means that it will check whether the input variables are equals to or unknown unequals to each other. They are not going to check the bit values of input variables, but the case equality and case equality check the every bit by bit inputs of the input variable. They also check the unknowns of the input variables. Therefore, the logical equality and inequality give the output unknown if any unknown appears at the input variable, but case equality and inequality check also these unknown variables at the input. So these are the logical equality and equality. Here is the output, same is the syntax to write the code in Verilog HDL. Here the output G, which checks whether A is logical equals to B or not. Two signs of equals to represent that it is logical. If three signs appear here equals, which means that it is case equality. So in case equality and equality, three signs appear, but in logical equality and equality, two signs appear. So it will check whether A is logical equals to B or not, because A is 4 and B is 7, so these inputs are not equal, so it will evaluate to 0. And then C, which is logical inequality between C and D. It will check whether C is inequality between C and D, so it will, because C is 0 1 0 and D is x 1 0, because unknown appears at the D input, so it is logical inequality. It will directly evaluate to unknown x. And then I, which is C inequality between C and F, it will check whether C is unequal to F or not, because C is 0 1 0 and F is xs 1 0, because here unknown appears and C is 0 1 0 and this is 0 0 1. Whatever are the unknown variables, C is always unequal to F, because here are the two least significant bits, which is 0 1 and C is 1 0. So whether here x are 0 0 1 1 or whatever, C will not always unequal to F, so it will evaluate to 1. And then D, which is case equality between D and E. It will check the bit inputs bit by bit between D and E and check whether this is case equal or not. C is D input is x10 and E input is x101. Whatever are these unknowns, because our these two bits are not equals, it is 0 1 and D is 1 0. Whatever are the input variables, these inputs are not going to equal, so this will give us to 0, not unknown. If this is logical equality, because unknown appears, so it will give us the unknown. Because this is case equality, so case equality will not going to give us unknown number, because it will give us 0 or 1, because this is equals, so it will give us to 0. Now we will perform the exercise for this case equality and inequality. This is our exercise. Now we have to write the code for this exercise in Verilog HDL. I have written the code for the equality operators. The syntax remains the same as all the codes. So name is equality operator, and here is the output and inputs. Then I have declared the inputs and output. Then I have assigned the output variables, which is A not equals to B, W, then X, which is C equals to D, logical equality, and then it is Y, which is E equals to logical equals to F, and then Z equals to G, which is case equality between G and H. The case equality will check the G and H bit by bit, and it will also check the unknown variables and give us the 0 and 1 output. Now I have compiled the software already. Now I will just make the waveform for the circuit. Now I have to give values to the input variables. Input A is 101, B is 010. Now I will give values to the A is 1 0 1, B is 0 1 0, C 0 1. Here I give the unknown value to the E. Now F is also 101x. I have given the values to all the input variable. Now I will just simulate this. Simulation starts. Here you can see the output screen of logical, because our output W is whether A is not equals to B. Because A is not equals to B, so our D is W output is 1. And next is X, which is C equals to D, because C is equals to D, so our output X is also 1. And then Y is, which is E equals to F, logical equality, and here in the input E and F the unknown variable appears, so the logical equality gave us the unknown. And similarly you can verify the outputs from our program and simplify it. So these are the logical operators. Now we'll see our next operators. Now our next operators are bitwise operator. Bitwise operators are negation and or XOR and XNOR operator. Bitwise operators perform a bit by bit corresponding operation on both operands. If one operand is shorter, it is bit extended to the left with zeros. Here you can see the example of bitwise operators. Now I will not tell you the syntax of the code. I have already told you that. I will just give you the explanation of bitwise. What is bitwise operator? Bitwise operators perform the operation in the input and between these bits. Means that our input A is 4-bit numbers. Bitwise operators perform the operations whatever it is, AND or XOR or negation. It will perform the operation between every bit of input variable A, means between 1 and 1, then answer of these with the 0 and then with the 0. Here you can see the AND A and C. Negation of A means that it will perform bit by bit operation between every bit of the variable A, and then A and C, it will perform the every bit operation between input variable A and C. Means that here the most significant bit of A is 1 and most significant bit is of C is 0. AND operation, so 1 this bit and 0 this bit will perform the AND operation. 1 and 0 is 0. Then next bit 1 and also 1 and AND operation between these bits. So in this way the bitwise operators perform work operation. Bitwise operators generally perform the operation between bit by bit, not the whole number. These can perform the operation between bit by bit between the input variables. Now I have to write the code for this exercise. I have written the code for the bitwise operators. Here I have assigned the output variables X, which is a negation of A, and then Y, which is or XOR operation between the input variables B and C, and bitwise. Bitwise operator will perform the bit by bit operation between the input B and C, means the it will perform every bit of operation between every bit of B and every bit of C. Means if it most significant bit of B is 1 and C is also 1, so it will perform the XOR operation between bit 1 and also C bit 1. Similarly for the Z output. Now I have already compiled that program and given the values to the input variables. Now I will show you the output waveform. Here you can see the output waveform of our program. Here the inputs are A, B, C and D and value of A is 0, 1 and X output is negation of A, means that our output will be negation of A, which is 1, 0. And next is bitwise operation between B and C XOR, means that it will perform the bit by bit operation between input B and C and XOR operation. So we will perform this XOR operation between 1 and 0 is 1, then 0, 0 is 0, then 1, 1 is 0, then 0, 0 is 0 and so on. This is bit by bit operation, bitwise operation. Similarly for output Z, which is OR operation. So 0 X, which is unknown, so 0, 0 X, which is unknown, 0, so 1 and unknown, because this is OR operation, so whatever the unknown, whether it is 0 or 1, the output will be always 1. So in this way we can perform this operation. Operators is reduction operator. Reduction operator perform in such a way that they take one operand and perform bit by bit next bit operation, starting with the two leftmost bits, giving only one bit result. Means that it will perform the operation between the one input. Means that if here I am giving the output D and perform the AND operation between the variable A, so it will perform the AND operation between every input of the bit. So between the input variable A, it will perform the AND operation between every bit of the input A. So 1 and 1, and it starts from the leftmost two significant bits. So it will start from the 1 and 1. 1 and 1 is 1. Here same as this. It is reduction operator, and at the final it will give us only one bit output. Similarly OR operation between every bit of the variable B, 0 or 1, then answer with the OR 0 and then so on with the 1, and evaluates to only single bit output. This is the reduction operator. Now we will see the Verilog code in the software. Here I have written the code for the reduction operator, and then compilation was successful. I already given the values to the inputs, and these are our outputs. So first of all, the output X is AND of A, so the AND operation between the every bit of A, so 0 and 1 is 0, so the output X is 0. And then output Y, which is OR of B bit, means that OR operation between every bit of input B. So 1, 0 is 1, 0, 1 is 1, and 1 and unknown, whatever our unknown variable bit is, it already gives 1 because it is OR. So our output Y is 1, and similarly output Z. So in this way we can perform the reduction operators. Now our next operator is shift operator. Here are the key symbols of the shift operator. Shift operator is basically shift left or shift right. The shift operator takes a vector and number indicating the shift. Basically it works in such a way that here I have assigned the output B, which is A less than 1. Basically it is not less than. It means that it will shift the every bit of A towards the right side, starting from the right side. So it will shift left by 1. It will shift every bit of A left and unit 1. So when we shift these 0 to this one and this 1 replaces this 0 and this 0 replaces this 1, and our output will be 0 1 0 0. And similarly output C, which is A greater than 2, which means that the out bit numbers of A will shift towards right and 2 units. So this 1 0 disappears and this 0 becomes the most least significant, and this one represents the bits 2, and your output becomes the 0 0 1 0. Now we will perform the exercise of this shift operator, which is shown here. I have written the code for the shift operator, same is the syntax as the previous codes, and then our output, which is x A equals to B shift 1. We can check whether A is equals to when B bits are shift towards right by 1 unit, and then our x output is 0 or 1 when A is equals to this or not. This means that first of all we have to shift the B bits towards right by 1 unit and then check whether it will be equals to A or not, and similarly for the Y output. Now we have to simulate this program and check the outputs. Compile the program and then give the values to the input variables and then check the outputs. Here you see that our input is 0 1 1 0, B is 1 1 0 0, and similarly C and D. You can see that our X output is whether check A equals to B when B we have shift B towards right by 1 unit, then check whether it is equals to A or not. First of all we have to shift B towards right by 1 unit, then the B becomes 0 1 1 0, and then this is equals to A, so our output X is 1. And similarly C, when we have to shift input D towards left by 1 unit and then check whether it is equals to C or not. Because it is not equal to C, so our output is Y is 0. So we can use these shift operators to check these operations. Then our next operators are concatenation. Concatenation key symbol is simple, this comma. Basically concatenation means that whenever I am assigned this D equals to A comma B, means that it will combine the A input with the B input. The bit numbers of A will appear first and then with the B. Similarly you can see here the output, 3-bit output, because A is 1-bit number and B is 2-bit number. I have written the code for the concatenation. Concatenation combines the two input variables. The variable which is written first, whose bits is written to is towards left, and then the second number. Here D, which is equals to A comma B, means that we have to combine the inputs A and B. So our A is 1, B is 0 0. So this is A comma B, so first input becomes the 1 and then 0 0. So our output will becomes 1 0 0, and then C, whose bits are 3 to 5. So we have to take the bit 1 0 and 1 and then combine it with the A, which is 1. So the output will become 1 0 1 1. So this is the concatenation in which we combine two numbers. So that's enough for today lab. Today we will see different operators in Verilog HDL and how we can use these operators to perform different functions and simulate it. So that's enough for today lab. Thank you.